Hi folks, in this section we're going to be going through types of problems called optimization problems. In each of these types of problems that you're going to see, we have two functions that are related somehow. One is the objective function, and this is the function that we are trying to either minimize or maximize. That's what we mean by optimize. And then the second function is a constraint function. So oftentimes our objective function has too many variables, and we can get them down to just one variable using our constraint function. It just relates the two variables or more variables in some way. So take a look at this example. We want to find positive numbers x and y satisfying the equation xy equals 12 such that 2x plus y is as small as possible. So our objective function is 2x plus y because that is what we're trying to minimize. And our constraint function is xy equals 12 because that's what relates x and y together. Okay, so take a second and pause the video and try to think of two numbers, x and y, that fit this description and try to make them, so when I say fit, I mean such that x times y equals 12. So try like 6 and 2. Do those numbers, if x is 6 and y is 2, is that the smallest that you can make 2x plus y?
Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
All right. If you tried integers only, you're close, but you're not going to make it as small as possible. I can make it smaller. So the way you can do it, I'll give myself a sheet of paper here. The way you can do it is, I know that x and y multiply to be 12, and I want to minimize, let me call this maybe z equals 2x plus y. Well, first of all, what I'll do is I will solve the constraint function so that I can replace y with 12 over x. And you could do the same thing, solve for x and replace x with 12 over y, either way. So that means my objective function now is 2x plus 12 over x. Now z prime, so if I take the derivative, I get 2 minus 12 over x squared. And the idea is, if I can solve this for 0, that'll give me my critical points. Or where this is undefined, where the derivative is undefined, would also be a critical point. But if x was 0, then y could be anything. We can't, well, I should say y can't be anything so that our constraint function would work. So knowing that x can't be 0 is useful. Okay, so now let me set it equal to 0 and solve. 12 over x squared. Of course I can subtract 2 from both sides. That gives me this, and then multiply both sides by -1 because I like positive numbers. Then maybe multiply both sides by x squared and divide both sides by 2. Gives me 6. So that means x must equal plus or minus square root of 6. But of course, the instructions were to find positive numbers, so x is square root of 6. Now, since I'm supposed to find both x and y, well, finding y is easy enough now that we have the constraint function. So a couple ways to do this. I can either just think about it. I can multiply by another square root of 6 to get 6, and then multiply by 2 to get 12. So that means y has to be 2 root 6, just looking at it. Or if I was being a little more careful, I would just solve my constraint function, plugging in root 6 y equals 12. Then y equals 12 divided by root 6, which doesn't look like what I got earlier, so you get a little nervous, but rationalize the denominator. And you see that you've got 12 root 6 over 6. These cancel to be 2. So you got 2 root 6. Okay, so those are my two positive numbers that minimize my objective function 2x plus y. That's as small as it can get. Now, you might be asked, what is that minimum value? And that minimum value is going to be 2 times root 6. So I'm just plugging in x and y into my objective function. 2 root 6. So the minimum value that that objective function could be is 4 root 6. And I can double check that that's a minimum by taking the second derivative of my function. So that is z double prime, and then plugging in the x value I got there. So that is 12 over x to the third, but times 2. That was 24 x to the third. And really all I care about is that I want to make sure that my function is concave up, so I'm actually getting a minimum. So if I plug x, the x value, square root of 6 in, all I care about is that this is greater than 0, and it is. So that means I was concave up. That means the critical point that I plugged in, this square root of 6, gave me a minimum value. Okay, let's look at another example. An 8-foot tall ladder. I'm going to give myself a sheet of paper here because I'm going to need to do some work here. An 8-foot tall fence, rather, runs parallel to the wall of a house at a distance of 3 feet away. So let me draw this, and notice this last sentence. Assume the house is extremely tall. I just don't want anything going over the house. So let's make an extremely tall house. I used to live next to one of these. Let's see. We'll say it has 4 floors. Alright, we've got a 8-foot tall fence here. And it sits, clearly not to scale, sits 3 feet away from the house. Now what I want is a ladder that extends to the house over the fence. Don't ask me why. A little worried about privacy concerns from my neighbor now. But the idea is we want a fence that'll reach the house, and I want to minimize the length of the fence. So in other words, how far out do I need to be? So if I call this bottom length x, then between the fence and the bottom of the fence will be x minus 3. Because 3 feet are taken up on the left side. And then just call the height y. And my ladder then, the length of my ladder is square root of x squared plus y squared. Alright, so I want to find the length of the shortest ladder that extends from the ground, over here, over the fence, to the house. So the idea being that it's going to be resting on the top of that fence. Alright, well notice I only have an objective function here, my ladder function. But my constraint function I can get from my picture. Because I can see that I've got similar triangles. My large triangle here, and this smaller triangle inside here, the 8 and the x minus 3. So if I set up a proportion, I know that 8 over x minus 3 is going to equal the same thing as y over x. Or, solving that for y, I get that y equals 8x over x minus 3. Alright, so that's my constraint function, and I can plug that in to my ladder function, my objective function. So this becomes x squared plus 8x over x minus 3 squared. Now looking at this, this is going to be just ugly when I take the derivative. So I'm trying to minimize this function, and it's going to be ugly. But I'm going to be a little sneaky here. It turns out if I minimize my ladder function, it would be the same, I get the same x and y value as if I minimize the square of my ladder. So I'm actually going to take the derivative of this instead. And that'll just look a lot nicer and be a lot cleaner to deal with. Alright, so the derivative, so let me call this L squared prime, is 2x plus, and let's chain rule this, 8x over x minus 3 times, now the derivative of the inside function, we still have to quotient rule this, so that is x minus 3 times 8 minus 8x all over x minus 3 squared. But this is going to clean up a little nicer. So that is L squared derivative 2x plus 2 times 8x x minus 3. Notice up here I'm going to have an 8x minus a 24 minus an 8x, so that's just going to become a minus 24 all over x minus 3 squared. Okay, so let's clean this up a little further. L squared is 2x plus, well, I can multiply 2 times 8 times 24, and I'll get, and it's a negative 24, so let me call this minus, I think that comes out to be 384 all over x minus 3 cubed, it looks like. Alright, so now I want to minimize this, so I'm going to set it equal to 0. Figure out where the critical points are, but if I set it equal to 0, so let me not skip too many steps here, 384 over x minus 3 cubed, well, I can multiply both sides by x minus 3 cubed just to get rid of that. Oh, and I'm missing an x, aren't I? I dropped this x off, so that should be up here and up here. But I can multiply both sides by x minus 3 cubed. Leaves me with 0 on the left still, but on the right I get this 2x x minus 3 cubed minus 384 x. The next thing I might do, just to simplify this, knowing that x is not 0, meaning my ladder is not right up against the house, then and I'll divide by 2x in both cases. So on both sides, I've got x minus 3 cubed minus, what is this going to be, 192. Or in other words, x minus 3 equals cube root of 192. So x is going to equal 3 plus cube root of 192 is 4 cube root 3. All right, so that's the x value. The distance away from the fence, of course, is just without the 3, the 4 cube root 3. I want to find the length of the ladder, though. So to do that, well, maybe I can find, not that I have to, I could plug in x into this, so I'm kind of doing 2 steps where I could just do 1, but I know that this is my y, 8x over x minus 3. So if y equals 8x over x minus 3, well, that is 8 times the x value I have, 3 plus 4 cube root 3 over 3 plus 4 cube root 3 minus 3. Of course, those 3's cancel out in the denominator. All right. This is clearly not pretty. 24 plus, what is this going to be? 32 cube root 3 over 4 cube root 3. And so now the ladder, I don't know why I've got a 4 there. The ladder is going to be, let's say ladder equals square root of 3 plus 4 cube root 3 squared plus, and I could divide, I could simplify this, I guess, pull out a 4 from both of those. So really you'll have 6 plus 8 cube root 3 over cube root 3 squared. Alright, that's the length of the ladder. If you want to get an approximation, plug it into a calculator, but I wouldn't be asking for it, and I'd be okay if you left it here. There's some simplifying you could do with the square. You can rationalize the denominator here, but let's leave it there. Okay, one more problem. A race has participants move from an initial point around a circular lake where they swim to some point. I should mention the radius of this lake is 1 mile. And they swim to some point across, past, I don't know, say a given point. They swim here and then they run the rest of the way. So the question is, how far, at what point should they meet the shore to where they start running? So they're going to swim to some point. What point should that be so that they minimize the amount of time of their race? Well, if this person swims at 2 miles per hour and then walks at 4 miles per hour, and I don't know why we're not running, but we are walking and swimming. So if we swim, where should we, or I guess I'm asking, what is the minimum time? Well, what do we know? Time is distance divided by rate. And if there's a rate of swimming, I'll call that 1. That means there's a distance for swimming and a distance that we're going to walk over our rate that we're going to walk. So, and we know the rates, but we want to figure out what is the distance for each of those. That's going to minimize our time. So I know my rate of swimming is 2 miles per hour, and my rate of walking is 4 miles per hour. So this is my objective function. Now my constraint function, it would be nice if I could get these distances to be related somehow. Well, one way to do that is to not actually get a function that relates the distance itself, or not look at that as the variable, but look at something else as the variable. So in particular, I'm going to look at the angle that I'm going to make with the start of the race to where I get out of the swim portion. All right, well, the distance here of the swimming, one way to look at that is cut this angle in half. That distance is going to be, that angle now is pi over 2. Sorry, not pi. Theta over 2 and theta over 2. But notice I make a right angle here. So the half distance is, half of that distance swimming is sine of theta over 2. All right, so my distance 1 is sine of theta over 2. Except I want, that only gives me half of the distance that I'm swimming. So I want the other half, which will be the same. So just multiply that by 2. So my distance is 2 times sine of theta over 2. All right. The distance that I walk, so the rest of this, notice, because I'm going halfway around this lake, this angle is pi minus theta. And just like we saw earlier, that amount could be ascribed to here when the radius is 1. So pi over theta is my second distance. All right, so I've got distance 1 and distance 2 related by theta. So I used a third variable, but I can write them both in terms of that. So my time is now 2 sine theta over 2 over 2 miles per hour plus pi minus theta over 4 miles per hour. All right, so what we want is, we want t prime in terms of theta. So let me simplify this guy a little bit. I can just take the derivative of sine of pi over 2, which is 1/2 cosine, I said pi again, theta over 2, plus -1 over 4 for the derivative of pi minus theta over 4. Pi being a constant, of course, so that is 0, and then minus 1 because the derivative of theta is 1. All right, now we want to know, where is that going to be 0? Where is that derivative 0? Well, let's just solve this equation. I'm adding 1/4 to both sides. So we have 1/4 equals 1/2 cosine of theta over 2. That becomes 1/2 is cosine of theta over 2. All right, so where is cosine going to be 1/2? Well, that is, of course, when your angle is pi over 3. 1/2 cosine, because sine of pi over 3 is root 3 over 2. Okay, so that means that pi over 2, theta over 2 rather, must be pi over 3, in which case theta is 2/3 pi. So if that's theta, then I can plug theta into my distance, or rather into my time equation. So that is, t is going to be sine of 2/3 pi over 2 plus pi minus 2/3 pi over 4. And this is going to come out to, well, this is sine of pi over 3, which we said was root 3 over 2. And this is going to be pi minus 2/3 pi is 1/3 pi, so this is going to be plus pi over 12. All right, so not the standard way we read hours, but there you have it. That's the minimum time to run this race. Okay, so some of these are more challenging than others, so it's important to try a wide variety of these optimization problems, but give them a shot and let me know if you have any questions.